Hi, welcome to another video, another class. In this chemistry class, we are having a quick revision, a rapid revision on yet another very important chapter from the 11th standard topic. As you can see, Unit 5, States of Matter. All of you are aware of what is the main topics dealt in the state of matter. It is gaseous state, gas laws, etc. Right? Straight away, let's start the topic. States of matter, primarily we deal with the three important states of matter: solid state, liquid state, gaseous state. Of course, there are several forms of states of matter we are dealing with, including plasma, various condensate, fermionic condensate, Bose-Einstein condensate, etc. The most stable, visible, experiencing, experimenting three important states of matter we deal in our subject level of study. It is solid state, liquid state, gaseous state, giving more importance to gaseous state in the chapter. Of course, at the end of the chapter, we are dealing with some of the properties of the liquids also, like surface tension, viscosity, etc. Right? Anyway, the starting portion of the unit dealing with the various intermolecular forces of attraction. The various intermolecular forces of attraction. That is the starting topic. Intermolecular forces of attraction. That is the initial topic dealt in the chapter. Various intermolecular forces, many of you know, almost different variety of intermolecular forces. One is called dispersion forces. Dispersion forces, also called London forces. Very popular, known as weak van der Waals forces of attraction. Dispersion forces. Very weak van der Waals forces of attraction when the molecules are coming close to somewhat 500 picometer vicinity. These forces are getting operated. Okay. And dispersion forces are given by two non-polar molecules. This is a non-polar molecule and this is another non-polar molecule. Between two non-polar molecules, due to their movement, due to their kinetic movement, etc., there can be a momentary polarization. There can be a momentary polarization in their symmetric electron density, which lead to an attraction caused between the molecules, especially when they comes to the close proximity, somewhat in the range of 500 picometer. There is an attractive force generated. We call it as weak intermolecular forces of attraction. We call it as dispersion forces, London forces. And the interaction energy is inversely proportional to 6th power of the distance between the particles. Suppose the distance between the particles is r. The interaction energy is inversely proportional to 6th power, the distance between the particles. So E proportional to 1 by r raised to 6. If you take hydrogen gas, if you take oxygen gas, all these are non-polar molecules. Between two non-polar molecules, there is dispersion force. Suppose you have two molecules A and B, and if they are non-polar molecules, the forces operating, we call it as dispersion forces, London forces, right? Number two, it is dipole induced dipole attraction. Dipole induced dipole attraction. What is meant by dipole induced dipole? Imagine you have a polar molecule and imagine you have a non-polar molecule. You have a permanently polar molecule and you have a non-polar molecule. This is a polar molecule and this is a non-polar molecule. This is having a dipole, as you can find. This molecule induces a polarity over here. So due to the influence of this molecule is getting induced, and there will be an induced polarity. This molecule also turn a polarization, and the attraction formed between the two molecules, we call it as dipole induced dipole. This is inducing a polarity over this molecule. That is dipole induced dipole attraction. Once again, the interaction energy is inversely proportional to proportional to R ratio, inversely proportional to R raised to 6, where R is the distance between the molecules. Suppose we take up a non-polar molecule, hydrogen, with a polar molecule with water. Imagine this is a polar molecule, this is a non-polar molecule. A polar molecule, hydrogen, or a non-polar molecule with a polar molecule, HCl. This is polar and this is non-polar. This is non-polar, this is polar. Between one polar molecule and one non-polar molecule, there is operating force is called dipole induced dipole attraction. So dispersion forces called London forces, dipole induced dipole attraction. Third one, that is dipole attraction. Third one, dipole attraction. What is dipole attraction? Imagine you have two permanently polarized molecules. Imagine you have two permanently polarized molecules. The forces of attraction between them is called dipole attraction. So this is molecule 1 having plus and minus. This is molecule 2 having plus and minus. The forces of attraction operating between them is called dipole attraction, which is going to be pretty more stronger. Right? But even then, the interaction energy comes out to be 1 by R raised to 6 for the polar moving molecules. That means in the liquid state and gaseous state, the polar molecules will have almost the same interaction energy. Meanwhile, stationary polar molecules means in the solid state. Stationary polar molecules, the interaction energy is proportional to 1 by R raised to 3. So that clearly indicates this is pretty more stronger compared to the other. So number 1, dispersion forces. Number 2, dipole induced dipole. Number 3, dipole attraction. And a special variety of dipole attraction, we call it as hydrogen bonding. A special type of dipole attraction, that is hydrogen bonding. This is a special case of dipole attraction. And hydrogen bonding is exclusively we find in the molecules like HF, in the molecules like H2O, in the molecules like ammonia, where we have hydrogen connected to the most electronegative fluorine, the second most electronegative oxygen, and the third most electronegative nitrogen. So in HF, you have hydrogen connected to highly electronegative fluorine. It can make a hydrogen bonding with the neighboring molecule. It can make a hydrogen bonding with the neighboring molecule. This is what called the hydrogen bonding. In hydrogen bonding, one part is hydrogen that is connected to fluorine, oxygen, nitrogen, which interact with the neighboring molecule, highly electronegative atom. If you take water molecule, it is HOH interacting with the neighboring oxygen molecule. This is hydrogen bonding. Hydrogen atom of one molecule connected to oxygen interacting with the neighboring highly electronegative oxygen atom. That is hydrogen bonding. If you take up ammonia, this is ammonia molecule. This is interacting with the neighboring molecule. So there can be a doubt, sir, is it HF only? Is it water only? Is it ammonia only? Can there be in between? It can be. Hydrogen bonding can be HO. It can be HOHF. It can be HOHN. See, all that combinations are possible. Hydrogen with oxygen, fluorine, oxygen, nitrogen. Hydrogen with fluorine, oxygen, nitrogen. With the fluorine, it will be a stronger bond. Meanwhile, extensive bonding is found in water molecule. Stronger bond is found in with the fluorine. Extensive bonding is found in water molecule. Right? So this is a special variety of dipole-dipole attraction, pretty more stronger, playing a vital role in deciding the property of many molecules, including the molecule which is vital for the living system, water molecule. The properties of water molecules are greatly governed by hydrogen bonding property. Not only in water molecule, various biomolecules, proteins, amino acids, and various molecules, hydrogen bonding plays a vital role. All the prominent properties of water which make it vital for the existence and survival of the life is caused by hydrogen bonding. So that is the importance of hydrogen bonding. So dispersion forces, dipole-dipole forces, dipole-induced dipole forces, hydrogen bonding. There is one type, ion dipole forces. Ion dipole forces. Ion dipole interaction. Imagine NaCl dissolving in water. Imagine NaCl dissolving in water. You know it is Na plus and Cl minus interacting with the water molecule. This is a dipolar system. This is a dipolar system which is interacting with ion, and that is called the ion dipole interaction. During the dissolution of ionic species, cations and ions dissolving in water molecule, there is ion dipole interaction. These are the various kind of intermolecular interactions that is dealt in the chapter. Meanwhile, we are switching on to a very important area which all of you know. Various properties, studies based on a unique platform for the gases, for gaseous system. We are going to have a unique platform study, a study on unique platform called the gas laws. With the properties of various gases dealt experimentally using gas laws. Various gas laws, that is our next topic. What are the various gas laws? Gas laws are basically a unique platform for dealing the properties of gases. We don't have such a unique platform for the study of solids. We don't have such a unique platform for the study of liquids, but we have for gases. What are the gas laws? All of you know. One is called Boyle's law. Boyle's law. What is Boyle's law? Boyle's law states that pressure of a given mass of gas is inversely proportional to its volume at a constant temperature. Pressure of a given mass of gas is inversely proportional to its volume at a given temperature. So temperature remain constant and number of moles remain constant. So when the amount of gas is constant for a given mass of gas, that means amount of gas is constant, temperature remain constant, pressure and volume are inversely related. When the volume decreases, pressure increases. When the pressure decreases, volume increases. When the pressure increases, volume decreases. They go inverse relation. When the pressure drops to half, volume increases to double. When volume becomes 4 times, pressure becomes 1/4, like that. So wherever there is a pressure increase in pressure, when the pressure increases, volume decreases, and vice versa for a given amount of gas at a constant temperature. The pressure of a given mass of gas is inversely proportional to the volume of the gas at a constant temperature. This is called a Boyle's law. P proportional to 1 by V. So you can write P equal to a constant K into 1 by V. That is PV equal to a constant. This is the condition for Boyle's law. P PV equal to constant. We can call it as equation of state. That is P1 V1 equal to P2 V2 equal to P3 V3 equal to so on. This is called the equation of state. Equation of state. That is Boyle's law. One of the very important law that we learned in the chapter. You must also go through the graphical representations of Boyle's law. How the graphical representations are coming? It is very famous called the PV isotherm. This is the graphical representation for Boyle's law. You have a rectangular hyperbola representing Boyle's law. PV diagram. This is rectangular hyperbola representing PV diagram. We call it as isotherm. Why it is called a isotherm? Since the temperature is kept constant, it is called a isotherm. Suppose this is temperature T1 at a particular temperature. You get a graph like this. Another temperature T2 which is greater than T1. What is the graph obtained? Please understand. T2 greater than T1, the graph will be on top. As the temperature increases, the graph go up like that. So greater the temperature, when you increase the temperature, T2 greater than T1, you will have a graph onto the upper side. Suppose I am maintaining a temperature T3 which is greater than T1 but less than T2. Then suppose I am taking a temperature T3 which is greater than T1 but less than T2, where the graph will be T3 graph. Where the T3 graph is going to be, T3 graph will be in between this. So this is T1, this is T3 and this is T2. T1, T3, T2. We can easily understand T1 less than, T3 less than, T2 like that. So as the temperature increases, the rectangular hyperbola position shift upward. As the temperature decreases, it comes down. Right? Or you can have the graphical representation P versus 1 by V like this. This is P versus 1 by V. P versus 1 by V. Directly proportional. Or you can have the graph Boyle's law PV versus P, a constant. PV equal to constant. P versus 1 by V like this. PV diagram like this. This is rectangular hyperbola. Isotherm. PV isotherm. This is P versus 1 by V and this is PV versus P. These are the different graphical representation of Boyle's law, which states that pressure of a given mass of gas is inversely proportional to its volume at a constant temperature. Is it clear? Now, the second one, we call it as Charles law. Second one, Charles law. Charles law, which states that volume of a given mass of gas is directly proportional to its absolute temperature at a constant pressure. Volume of a given mass of gas is directly proportional to absolute temperature at a constant pressure. So pressure remain constant, of course number of moles remain constant. Whenever we say for a given mass of gas, that means the mass is constant. When the mass is constant, number of moles is constant. So I repeat, Charles' law states that volume of a given mass of gas is directly proportional to absolute temperature. That means temperature in Kelvin scale, not in degrees Celsius. For a constant pressure condition. So we can write V is equal to a constant into T or V by T equal to constant. That is Charles' law. V by T is equal to constant. That is V1 by T1 equal to V2 by T2. So on. Equation of state once again. So when the temperature doubles, volume doubles. So when the temperature increases, volume increases. When the temperature decreases, volume decreases. So on. so on. When the temperature doubles, volume doubles. Temperature T1 equal to 30 degrees Celsius and volume V1 is equal to 1 liter. Temperature T2 equal to 60 degrees Celsius. Don't ever say that volume V2 equal to 2 liters. Don't ever say that. Why? That's what I said. Volume is directly proportional to absolute temperature. That means temperature in Kelvin scale. See, the temperature becomes double, but that is in degrees Celsius. When you take in Kelvin scale, it is 273, it is 303 Kelvin, and here it is 333 Kelvin. Is it double? Is it double? No. It is the Kelvin scale that is to be taken into consideration. So when the temperature doubles, volume doubles. For what? Kelvin scale temperature. Suppose you have such a condition. Suppose you have such a condition. Volume V1 equal to 1 liter, temperature T1 equal to 200 Kelvin, and temperature T2 equal to 400 Kelvin. Asking you what is volume V2? No doubt, 2 liters. Now the temperature is doubling in Kelvin scale, volume will be doubling in condition. So don't make any mess up with the degree Celsius measurement. It should be in Kelvin scale. That is Charles' law. Volume of a given mass of gas is directly proportional to absolute temperature. You can have a Gay-Lussac modification for Charles' law. Gay-Lussac's modification. Pressure of a gas is directly proportional to absolute temperature when the volume is kept constant. See, the point is very simple. We have 4 parameters: pressure, volume, temperature, and number of moles. Two will be variable, the other 2 will be constant. Pressure and temperature are variable, while volume and number of moles are constant. This is Gay-Lussac's modification for Charles' law. P proportional to T at a constant volume. V proportional to T at a constant pressure. So you can very well write P by T is equal to constant, P by T equal to constant, or P1 by T1 equal to P2 by T2, so on, equation of state. There is another way giving a relation with the degree Celsius condition. That is nothing but volume of a gas increases or decreases by 1 by 273 part of its original volume at 0 degrees Celsius for each degree rise or lowering of temperature. I will repeat. Volume of a given mass of gas. Volume of a given mass of gas increases or decreases by 1 by 273 part of volume at 0 degrees Celsius. This is volume at 0 degrees Celsius, V0. It increases or decreases by 1 by 273 of V0 for each degree rise in temperature and lowering in temperature. Suppose temperature is rising, you will take plus. Suppose temperature is lowering, you will take minus. So Vt, that is volume at T degrees Celsius, Vt, volume at T degrees Celsius, will be V0 plus or minus V0 by 273 into T degrees Celsius. Suppose the temperature is rising. Suppose the temperature is rising, you will take plus. Suppose the temperature is lowering. Suppose the temperature is lowering, you will take minus. Suppose there is a 10 degree rise. Suppose there is a 10 degree rise, you will calculate V0 plus V0 by 273 into 10. Suppose 10 degree lowering, it will be minus. Suppose it is 273 degree lowering, what will happen? 273 degree lowering, what will be happening? That is V at minus 273 Kelvin. See, we are referring from 0 degree. 273 lowering. What will happen? It is V0 minus V naught by 273 into 273 lowering as it is minus. It will cancel V0 minus V0, you get 0. And that is called absolute zero. Absolute zero. Volume becomes zero at absolute zero. This is how the Kelvin scale has been fabricated. Kelvin scale fabricated on this ground. You see that this is volume and this is temperature in degrees Celsius and this is zero. Volume, temperature decreases, volume decreases. Temperature decreases, volume decreases. You see the graph is coming like this. When the temperature is zero, volume is not zero. You see, temperature zero, volume is not zero because this is in degrees Celsius. And thereby, the fabrication of the new scale, Kelvin scale, has been done, where the extrapolation of this graph, this is experimentally done on negative side, and upon extrapolating, we got the zero volume condition, and that is minus 273.15 degrees Celsius. We call it as zero Kelvin. We call it as absolute zero. Kelvin scale context is derived on this ground using Charles law. So, Boyle's law number 1, Charles law number 2. Right? Next is Avogadro's law. Avogadro's law. So, Boyle's law talking about pressure-volume relationship. Charles law talking about volume-temperature relationship. Already we have gone through Gay-Lussac's modification, pressure-temperature relationship. Next is Avogadro's law, which all of us know. Equal volume of all gases under the same condition of temperature and pressure contains equal number of molecules. That is Avogadro's law. Equal volumes of all gases under the same condition of temperature and pressure contains equal number of molecules or moles. That is Avogadro's law. Suppose you are taking, say, X liters of hydrogen gas, the same X liters of oxygen gas, the same X liters of carbon dioxide. All these sampled under the identical condition of temperature and pressure contains equal number of molecules. If there are n molecules here, the number of molecules here will be n, and the number of molecules here will be n. If the number of moles here is small n, number of moles here will be same, small n. Number of moles here will be same, small n. So, equal volumes of all gases under the same condition of temperature and pressure contains equal number of molecules, equal number of moles. Right? And suppose under the same condition, I am taking 10x liters of nitrogen. How many molecules will be there? How many moles will be there? X liter contain n molecules, therefore 10x liter contain 10 n molecules. X liter contain n molecules, therefore 10x liter contain 10 n molecules. So we can write volume is directly proportional to number of moles or number of molecules, provided temperature, pressure remain constant. So, pressure volume relationships is Boyle's law, volume temperature relationship is Charles law, or pressure temperature relationship Gay-Lussac modification, and here volume number of moles relationship, that is Avogadro's law. Right? So, what are the three laws? It is P proportional to 1 by V, Boyle's law, right? And V proportional to T, Charles law, or we can say P proportional to T, Gay-Lussac modification. So, P inversely proportional to volume at a constant temperature and number of moles. B directly proportional to absolute temperature at a constant pressure and number of moles. or pressure directly related to absolute temperature when volume and number of moles are fixed. And finally, V directly proportional to N. V directly proportional to N at a constant temperature and pressure. So we can have a correlation. What correlation? V proportional to 1 by P, V proportional to T, V proportional to N. We can write V proportional to NT by P, or PV proportional to NT, or PV equal to nRT, where R is called, all of you know, universal gas constant. It is a constant of proportionality. PV equal to nRT, which is obtained as a combined gas equation. It is obtained as a combined gas equation. PV equal to nRT. What is P? P the pressure. What is V? The volume. And N, number of moles of the gas. And R is called a universal gas constant. Universal gas constant, the value of which depends on the unit of pressure and volume, and T, the temperature in Kelvin scale. You must know, you must by heart the units and values of the universal gas constant R. What are the different values? You get it from the textbook. The different values. The most commonly encountered value of R is 0.0821 liter ATM per Kelvin per mole, or it can be 8.314 joule per Kelvin per mole. This is most commonly utilized two values, 0.0821 liter ATM per Kelvin per mole and 8.314 joule per Kelvin per mole. Remotely in certain numericals, we may be encountering approximately 1.98, approximately 2 calorie per Kelvin per mole. Calorie per Kelvin per mole. So these different units of R value, which depends on the unit of pressure and temperature, also you must go through. It is enlisted in the textbook. You must by heart that value and be very careful applying the value of R according to the unit of pressure and volume that has been chosen. And also there comes a question, what is the physical significance of the universal gas constant R? What is the physical significance of universal gas constant R? What is it basically? It is basically nothing but pressure volume work. It is pressure volume work. You see the unit, it is joules. It is calories. Liter ATM, that is the unit of energy. That's a unit of work. So R is basically nothing but work done per Kelvin per mole. Work done per Kelvin per mole. That is the physical significance of universal gas constant R. And the equation what we have learned, PV equal to nRT. Very popular known as, yes, what is it called? It is called a universal gas equation or ideal gas equation. This is ideal gas equation. PV equal to nRT, popularly known as ideal gas equation. Every gas can adhere to such an equation under ideal conditions. What is the most preferable ideal condition? You might have learned about what is the most preferable ideal condition. It is a low pressure and high temperature. Low pressure, high temperature condition, every gases tend to be ideal, obeying Boyle's law, pressure volume inverse relationship, obeying Charles' law, volume temperature direct relationship, absolute temperature, Gay-Lussac modification, pressure temperature relationship, and Avogadro's law, volume number of moles relationship, right? All these consolidated together to make ideal gas equation, and we can have ideal equation for state. How's the ideal equation for state will coming? Consolidating all, we can have P1 V1 by T1 equal to P2 V2 by T2 equal to so on. That is equation of state. Equation of state we were applying in Boyle's law, Charles' law, Avogadro's law, everywhere we were applying the equation of state. So we have been able to study the properties, the behavior, the characteristics of gases in a uniform platform, and that platform is called a gas laws, and gas laws consolidated to get ideal gas equation. Any gas under the given condition, when it obeys Boyle's law, when it obeys Charles' law, when it obeys Avogadro's law, and when it obeys ideal gas equation, we call them ideal gases. Also keep it in mind, there is no gas which is perfectly ideal. It is only a condition. It is a condition of behavior that is called ideal gas behavior. And ideal gas behavior is prominently observed when the pressure is very low and the temperature is very high. Sir, what happens when the pressure increases? Sir, what happens when the temperature decreases? Of course, obviously, every gases will tend to make their own deviation in the behavior, and we call them as real gases. They are called real gases. All gases are basically real gases. When do they show their real behavior? When the pressure increases, they show their real behavior. When the temperature increases, they show their real behavior. And I am aware of, I think all of you are aware of, we are talking about van der Waals equation for real gases. On the later part of the chapter, we are going to discuss on that. So this is about gas laws and ideal gas equation, right? Another very important topic that we need to discuss from the context is Dalton's law. Dalton's law of partial pressures. Dalton's law of partial pressures. Dalton's law of partial pressures. Which suggests that the total pressure of a mixture of two or more non-reacting gases. Suppose we have two or more non-reacting gases taken in a chamber. We have gas A, gas B, gas C, for example. Three gases are there which are non-reacting gases. Say, for example, hydrogen, oxygen, and say carbon dioxide. Just assume these are the three gases which may not react between each other. Sir, hydrogen can react with oxygen. No, they don't react under normal condition. Hydrogen can react with oxygen producing water only under specific reaction conditions, not under normal condition. Normal condition, they don't react. Okay, so I have taken a non-reacting gases, hydrogen, oxygen, carbon dioxide. The law states that the total pressure exerted by the gases in the vessel will be the sum of partial pressures of individual gases present. Suppose the partial pressure offered by A is PA, and that of B is PB, and that of C is PC. The law states that, Dalton's law states that the total pressure offered by the gas, the total pressure offered by the gas is equal to partial pressure of A plus partial pressure of B plus partial pressure of C. Suppose A is offering a pressure, say 0.2 atm, and B is offering a pressure, say 4 atm, and C is offering a pressure, say 6 atm. The total pressure will be 0.2 plus 4 plus 6, it will be 10.2 atm. That is Dalton's law. So Dalton's law states that the total pressure offered by a mixture of two or more non-reacting gases. What if it is a reacting gas? Suppose we are taking in a chamber dry ammonia gas and dry HCl gas. Just imagine, Dalton's law may not be applicable because the moment they meet, they react. Ammonia, when meet with HCl, you get white fumes, ammonium chloride, in which case you can't apply Dalton's law. So Dalton's law is applied over such an example where you have a mixture of non-reacting gases. The total pressure exerted by a mixture of two or more non-reacting gases will be the sum of partial pressures of individual gases. Now comes a question, what is meant by partial pressure? Partial pressure means, imagine you take an identical chamber. Imagine you take an identical chamber where hydrogen alone, this gas alone is taken. The gas A, that is hydrogen, alone taken under identical condition, same volume, same temperature. Then the pressure offered by A is called the partial pressure of A. Suppose the amount of gas here available inside the chamber alone under the same temperature, that pressure offered by A is called a partial pressure. The pressure offered by individual gases under same condition is called a partial pressure. So the total pressure of a mixture will be sum of partial pressures of individual gases, right? You must be able to know the relationship regarding the Dalton's law formula, Dalton's law formulation. All of you know PV equal to nRT, that is P is equal to nRT by V. Suppose I am taking individual gases, PA is equal to NART by V, PB is equal to NBRT by V, as the temperature and volume are fixed. We are taking in a particular chamber, so volume is fixed and identical condition, temperature is fixed. What varying is number of moles. So what happens? PC is equal to NCRT by V. And what is P total? P total is equal to PA plus PB plus PC. That is Dalton's law. So what do you get? P total is equal to this plus this plus this. So what you are getting? NA plus NB plus NC into RT by V. Isn't it? P total will be NA plus NB plus NC into RT by V. Now imagine you are taking the ratio between, this formula and this formula. What do you get? You get PA divided by P total is equal to NART by V divided by NA plus NB plus NC into RT by V. Isn't it? Now this gets cancelled. You get NA by NA plus NB plus NC. I'm sure everybody know this is nothing but mole fraction. So it is PA by P total equal to mole fraction of A. A very, very important relation connecting Dalton's law of partial pressure, right? Similarly, PB is equal to, PB by P total equal to mole fraction of B. PC by P total is equal to mole fraction of C, like that. Or partial pressure of a component will be, partial pressure of one component is equal to PA is equal to mole fraction into P total. PA is equal to mole fraction of A into P total. PB is equal to mole fraction of B into P total. PC is equal to mole fraction of C into P total. Like that. Very, very important relation connecting Dalton's law of partial pressures. A very important relation. So far we were coming through the intermolecular forces of attraction, gas laws, Boyle's law, Charles law, Avogadro's law, Gay-Lussac modification, ideal gas equation, and now Dalton's law of partial pressures. Another very important formulation you must remember, many times problems based on which we encounter is the density relation. Density relation. Density formula. We know PV equal to nRT, ideal gas equation, and that is equal to W by M RT, where the number of moles is mass by molar mass. Number of moles is mass by molar mass. So we can write P is equal to W by V RT by M. And I am sure you understand this is density. So it is P is equal to dRT by M or density D. Density D is equal to Pm by RT. This is a very important formulation. Many times we encounter problems based on this. Density relation for ideal gases. Very simple formulation, right? So far we were going through all the way in the NCERT. We can see these are the topics we have seen. Intermolecular forces of attraction, as I was explaining earlier, dispersion forces, London forces, etc. All these things we have seen. Just let's have a review. Gas laws, all gas laws we have seen. Isotherm, this graphical representation. Hope you remember this formula which we have gone through, Charles law. Charles law graphical representations. Charles law graphical representation also we have seen. So-called isobar. Isobar. Absolute zero we have seen. Isocore. Isotherm means constant temperature. Isobar means constant pressure. Isocore means constant volume. All of you know. And ideal gas equation. The unit of R and the values of R. Already it was explained. These are the data which I asked you to review. The values of R. 8.314. Pascal meter cube per Kelvin per mole. 8.314 10 power minus 2 bar liter per Kelvin per mole. 8.314 joule per Kelvin per mole. 0.0821 or 8 point something 10 power minus 2 liter ATM per Kelvin per mole. One more data I have given. 1.98 approximately 2 calorie per Kelvin per mole. All these values depends on the unit of pressure and volume. Dalton's law, we have seen Dalton's law. And regarding Dalton's law application, this is a very important thing. Dalton's law application. Imagine we are talking about the pressure of air. You please understand, the pressure of air can be related like this. It is P total, that is the pressure of air, minus aqueous tension, that is the pressure of dry gas. What is meant by this aqueous tension? It is the pressure offered by vapor particles. This is the pressure offered by vapor particles. So pressure of air will be equal to pressure of dry air plus aqueous tension. So what is pressure of dry air? P total minus aqueous tension. Weather related approaches and calibrations, we make use of this aqueous tension. This is also an application of Dalton's law. And one more relation we have gone through, density relation, density relation. So I was just reviewing the main points and aspects connecting what are there in the NCERT, whether we missed some points or not. Now, another important point is kinetic molecular theory. Kinetic molecular theory of gases. Very, very important. Kinetic molecular theory of gases. There are some 5-6 important points which we need to go through. Number one, This is the number 1 point. Gases consists of large number of identical particles, atoms or molecules that are so small and far apart on an average that actual volume of the molecule is negligible compared to the empty space between them. Gaseous matter made up of tiny particles, we call it as point mass. Tiny particles. And they are available in such a way that the volume of single molecule is negligible compared to the interparticle distance. That is the conclusion by kinetic theory of gases. Whenever this conclusion is applicable for a gaseous system, it will behave ideally. And at times, as I was commenting earlier, when the pressure increases, the molecules when comes close, they may show actual behavior. We call it as real gas behavior, right? Second one, there is no force of attraction between the particles. There is no force of attraction between the particles. Of course, the particles, when they are far apart, there is no force of attraction, right? What about when they are coming close? Suppose they are coming close to the range of 500 picometer range. The molecular attractions start operating and the ideal behavior deviated to real behavior, okay? Then they are under constant random motion. Molecules are under constant random motion, during which they collide with each other. They collide with the walls of the container, and that comes as a measure of pressure. The forces applied over the walls of the container by collision per unit area is called pressure, right? Kinetic theory is commenting some very important kinetic molecular model of gaseous system. Then they are moving in all possible direction. They collide with each other and also with the walls of the container. The collisions of gas molecules are perfectly elastic. There is no loss of energy. The molecular collisions are perfectly elastic. And before and after collision, they travel in straight line. Not necessarily always. Suppose the molecules are coming very close and there is a molecular attraction, not necessarily they may travel in a straight line always, but normally speaking, the molecules are traveling in straight line before and after collision, as there is no force of attraction between them, right? And the energy of molecules before and after collision remain the same. Suppose two molecules collide, and if the velocity, the energy of one molecule decreases, consequently the velocity, energy of the next molecule will increase, so that the average energy will remain fixed at a particular temperature. And the main commitment made by the system, made by the theory, is that the average kinetic energy is always a function of temperature. The average kinetic energy of gaseous molecules is a function of temperature. Similarly, molecular velocity. Maybe different molecules moving with a different velocity. Even if initially the molecules are moving with the same velocity, their velocity will change abruptly because they undergo random collision. Due to collisions, molecular velocity will keep on changing. But on an average, what happens is, if the velocity of one molecule after collision increases, consequently the velocity of the other colliding molecule velocity will decrease, so that the average remains the same. So the average kinetic energy will be a function of temperature, right? So 6 or 7 important points are commented by kinetic theory of gases. It is kinetic molecular model of gases. It is so called, and is presenting a very important equation, the so called kinetic gas equation. Kinetic gas equation. PV is equal to 1 by 3 mn u square. PV equal to 1 by 3 mn u square. What is P? Pressure. V? Volume. What is M? M stands for mass of one molecule. M stands for mass of one molecule. And N stands for number of molecules. M stands for mass of one molecule. N stands for number of molecules. And what is U? U is molecular velocity. U is molecular velocity. There are 3 types of molecular velocity. We are going to have a detailed talk after this. most probable velocity, average velocity, RMS velocity. We will have a talk on that after this explanation. So there are three different kinds of molecular velocity. Most probable velocity represented by alpha, average velocity represented by nu, and RMS velocity represented by u. These three molecular velocities we are going to discuss in detail. Before that, let me explain this kinetic gas equation. So PV is equal to 1 by 3 mnu square. Suppose we are taking 1 mole of gas. Suppose we are taking 1 mole of gas. We can say PV is equal to 1 by 3 m into Avogadro number u square. Right? What is Avogadro number? We know 1 mole gaseous molecules because I am talking about 1 mole gas. For 1 mole gas, number of particles will be Avogadro number. Now, what this becomes? Mass of 1 molecule into Avogadro number of molecules will be mass of Avogadro number of molecules. Mass of Avogadro number of molecules is molar mass. Mass of Avogadro number of molecules, that is molar mass. So what do you get? PV equal to 1 by 3 mu square, where m is molar mass. Is it clear? Right. So now I am going to make a small modification in this. I am going to write. See, it is half into 2 by 3 mu square. I am making a small rearrangement mathematically. See, both are same. 2 cancels, you get 1 by 3 mnu square. Right? So this is basically I wanted to write 2 by 3 into half mu square. You know this is kinetic energy. Half mu square is kinetic energy. So what do you get? PV equal to, see, this and this are same. 2 will cancel 1 by 3. So this is 2 by 3 into half mu square. Half mu square means kinetic energy. So it is PV is equal to 2 by 3 into kinetic energy. We call it as average kinetic energy because we can't talk about individual kinetic energy which keep on changing. And PV, you know, it is equal to RT. So RT is equal to 2 by 3 into kinetic energy. Therefore, kinetic energy is equal to 3 by 2 RT. This is a very important derivation and relationship based on kinetic molecular model of gaseous system. Kinetic energy average kinetic energy is equal to 3 by 2 RT. This is what I have commented earlier, and that is from the theory itself. Kinetic energy is directly proportional to temperature. Kinetic energy of a gaseous system is directly proportional to absolute temperature. Hope you understand the derivation. PV is equal to 1 by 3 mnu square. M is mass of 1 molecule, n is the number of molecules. Suppose I am taking 1 mole gas, number of molecules will be Avogadro number. So, mass of Avogadro number of molecules, that is molar mass. So, it is 1 by 3 mu square. Now, I am making a small mathematical adjustment. I am writing 3 by 2 into 1 by 2. 2 will cancel, 1 by 3, same thing. Just for a mathematical adjustment to express in terms of kinetic energy. So, I am getting PV equal to 2 by 3 half mu square. That is, PV is equal to 2 by 3 into kinetic energy. Therefore, kinetic energy is equal to 3 by 2. PV replaced by RT. Because for 1 mole gas, PV equal to RT. For 1 mole gas, PV equal to RT. So, we can write kinetic energy is equal to 3 by 2 RT. Kinetic energy directly proportional to absolute temperature. I hope it's clear. Right? And for n moles of gas, what will be the relation for n moles of gas? For n moles of gas, kinetic energy is equal to 3 by 2 nRT for n moles of gas. What about 1 molecule of gas? What about 1 molecule of gas? It will be 1 molecule. For 1 molecule, it will be kinetic energy is equal to 3 by 2 R by Na into T. This R by Na is called a Boltzmann constant, Kt. So, kinetic energy is equal to, for 1 molecule, kinetic energy is equal to 3 by 2 Kt, K called a Boltzmann constant, ratio between R by Na, gas constant by Avogadro number. These are some important relationships which you need to notice from kinetic theory of gases. I do remember I told you we will discuss in detail what are the molecular velocities. Now a talk on various molecular velocities. Various molecular velocities. What are the important molecular velocities? Number one, most probable velocity. Most probable velocity. Most probable velocity, I am indicating with a symbol, say alpha. Most probable velocity means velocity possessed by maximum fraction of molecules. Velocity possessed by maximum fraction of molecules. Suppose along the y-axis we have fraction of molecules and along x-axis we have velocity. There will be Maxwell distribution diagram. This is so-called a Maxwell distribution diagram coming like this. You can find the maximum fraction of molecules moving with a particular velocity. That is called the most probable velocity. Velocity possessed by maximum fraction of molecules. That is most probable velocity. Mathematically, alpha is equal to most probable velocity, or you can write U most probable velocity, no issue. It is equal to root of 2RT by M. Remember this. Most probable velocity expression. It is root of 2RT by M. Now the next velocity term, that is average velocity. Second one, average velocity. I am expressing with the term nu, or you can write U average. Either way, the term is not important. Average velocity. What is average velocity? Very simple, mean velocity. Suppose there are n molecules. Suppose there are n molecules moving with the velocity, say C1, C2, C3 up to Cn divided by n. This is average velocity. Just average. That is average velocity. Suppose there are n molecules moving with the velocity individually, C1, C2, C3, they are velocities of individual molecules. First molecule moving with the velocity C1, next molecule moving with the velocity C2. So C1 plus C2 plus C3 plus up to Cn divided by n. That is average velocity. Mathematically, average velocity is equal to root of 8RT by pi m. That is average velocity. And last one, the most encountered one, RMS velocity, root mean square velocity. Root mean square velocity. RMS velocity. Root mean square velocity represented by U or U RMS. Root mean square velocity. What is root mean square velocity? Root of square of the mean. That's it. So URMS will be root of C1 square plus C2 square plus C3 square up to Cn square divided by n. Root mean square velocity. That is RMS velocity. Right? And mathematically URMS is equal to root of 3RT by m. Root of 3RT by m. Please don't forget. Most probable velocity, average velocity, and RMS velocity. Most probable velocity, average velocity, and RMS velocity. The three important velocity terms. And this is most probable velocity. Where comes average velocity? Please understand the ratio between alpha is to nu is to u. That is most probable versus average versus RMS velocity. It is coming 1 is to 1.128 is to 1.224. This is the ratio. So compared to most probable velocity, average velocity will be slightly greater. And compared to which RMS velocity will be again slightly greater. That means you can express in the graph itself. This is most probable velocity. Therefore, average velocity will be somewhere here. This is average velocity. RMS velocity will be again somewhere here. This is RMS velocity. And the diagram is called a Maxwell distribution diagram. This is at a particular temperature T1. When the temperature increases, what is the change in graph? That also you must understand. What happens when the temperature increases? Velocity will increase. So what happened to the graph? When the temperature increases, this is fraction of molecules. This is fraction of molecules. And this is velocity already drawn. And this is the graph at a temperature T1. And this is most probable velocity. And this is average velocity. And this is RMS velocity. Now, what happens if I am increasing the temperature? When you increase the temperature, see what happens. The graph goes like this. This is at a temperature T2. The graph becomes more broader. The peak is shortened and it becomes more broader so that the area under the graph remains same. Area under the graph remains same. But you can see that peak is coming to right hand side. Now the most probable velocity is here. This is the most probable velocity. The fraction of molecules decreases. Fraction of molecule decreases and the velocity increases. This is the most probable velocity now. And this is the average velocity now. And this is the RMS velocity now. So all the velocity terminology, the values will increase upon increasing the temperature. I hope it is pretty clear. So three important velocity terms, that is to be noted from the kinetic theory explanation. Right? We are talking about ideal gases. So ideal gases will be the one which follows kinetic molecular model. Ideal gases is the one which follows kinetic molecular model. Mainly two important aspects. What are the two important aspects? Volume of a molecule is negligible compared to the intermolecular distance. Number one. There is no force of attraction between the gaseous molecules. Number two. Whenever this condition is strictly obeyed, it will be obeying ideal gas equation. It will perform like an ideal gas, which happens at a low pressure and a high temperature. So what if the pressure increases? What if the temperature decreases? The gases behaving real gases. There is no gas which is perfectly ideal. All gases are real gases. Considering this molecular attraction and real gas behavior, Van der Waals explained real gas equation. Maybe most of you remembering what is Van der Waals real gas equation. Real gas equation introduced by Van der Waals, called Van der Waals equation. Van der Waals equation. And the equation explained is P plus AN square by V square into V minus NB equal to nRT. This is real gas equation. This is Van der Waals equation. P plus AN square by V square into V minus NB is equal to nRT. This is for countering or a correction factor included for the real gas character, including molecular attraction, molecular volume, etc. So the ideal gas equation PV is equal to nRT is corrected in this format. Now pressure incorporated with a correction term. Pressure incorporated with a correction term. This is the correction term for pressure. And this is the correction term for volume. This is called a correction pressure. This is called a correction volume. Right? So this is known as correction pressure. Correction pressure is equal to AN square by V square. And the term this A, that is called A and B, called the van der Waals constants. A and B called the van der Waals constants. Van der Waals constants. What is the significance of A and B? A is a measure of molecular attraction. A is a measure of molecular attraction and B is related to molecular volume. A related to molecular attraction, B related to molecular volume. Now you see, correction pressure is equal to AN square by V square. So what is A? What is A? It is P correction into V square by N square. So what is the unit of A? It is pressure unit, bar or ATM into volume unit, liter square by mole square. This is the unit of A, van der Waals constant A, ATM, liter square, mole inverse square. Unit of A. Then what is the unit of B? What is the unit of B? This is called a correction volume. This is called a correction volume is equal to NB. Therefore, what is B? B is equal to V correction by N. That is liter per mole. That is a unit of B. So understanding unit of A and B van der Waals constant is very important. And understanding the real gas equation is very important. Right? It is P plus AN square by V square into V minus NB is equal to nRT. Is it clear? P plus AN square by V square into V minus NB is equal to nRT. That is the relation. And there can be, according to increase in pressure, increase in volume, increase in temperature, varying conditions, we can have various manipulations over this real gas equation which we can encounter in the questions that we are discussing in the classes. This is real gas equation for n moles of gas. For 1 mole of gas, it will be P plus A, N square is not required, P plus A by V square into V minus B equal to RT for 1 mole of gas. For 1 mole of gas. Right? So these are conditions pertaining to real gas equation and its characters. And see this graphical representation, very important, this graphical representation. This is PV diagram, PV versus P diagram, and this is ideal gas. The previous sessions in the regarding the discussion of Boyle's law, we were discussing the graphical representation for Boyle's law, PV versus P graph. PV versus P graph, a straight line. This is ideal gas. And you see, all gases, whether helium, hydrogen, methane, carbon monoxide, they start from ideal point. But that is at a low pressure. At a low pressure, they start from ideal point. But when the pressure increases, they deviate. And these characters are called real gases. They were actually starting from this point, but unable to travel through the straight line. As the pressure increases, they show their own character. You see hydrogen, it goes like this. Helium, hydrogen go like this. Carbon monoxide coming like this. Methane coming to negative deviation and then going to, it shows like this. This is called a real gas behavior, which can be understood, explained by real gas equation, van der Waals equation. Right? And there we have one more plot which clearly indicates, that is PV diagram. PV diagram, you see real gas, this is real gas diagram, this is ideal gas diagram. They are coming almost same together at a low pressure. This is low pressure region. At a low pressure region, the real gas and ideal gas are merging. You see that they are same. As the pressure increases, they start showing their own character. And it is evident that ideal gas volume is less than real gas volume. ideal gas volume is less than real gas volume, right? And that is what we have seen. V ideal is equal to V real minus ideal gas volume is less than real gas volume. Real gas volume is greater. V real minus NB. This is the correction factor which we have seen. So real gas volume is greater. Real gas volume is greater. You see, real gas volume is greater because real gas pressure is lower. Real gas volume is greater because real gas pressure is lower. Why the real gas pressure is lower? See, this is evident that Vi less than V real. Why? Because Pi is greater than P real. P real is lower. The real pressure is lower. Why the real pressure is lower? Because molecules, we are talking about real gas. What is the speciality of real gas? Real gases, molecules attract each other. When they attract each other, their ability to hit on the walls of the container freely will decrease. That means the pressure will decrease. Right? I will demonstrate. Suppose this is a vessel and imagine these two are ideal gas molecules. This is ideal gas molecules and this molecule is freely hitting on the walls. Imagine it is real behavior. In real behavior, see now the molecules does not interact each other. Real gas means the molecules does not interact each other. What about ideal? Ideal molecules, they does not attract each other. Kinetic molecular theory. Ideal molecules does not interact with each other. Ideal gas means there is no molecular forces of attraction. But when the molecules come close, when the pressure increases or when the temperature decreases, when the molecules come close, there is molecular attraction starts operating. Now what will happen? This molecule will not be able to make a free hit. This molecule is influenced by this molecule. This molecule will drag and therefore the molecular hitting will not be a free hitting. It is going to be a interacted one and the pressure hitting, the force exerted on the walls will decrease, pressure will decrease. So real pressure will be lower than ideal pressure. Consequently, real volume will be greater than ideal volume. And you see what the correction factor we do? P plus AN square by V square. So P ideal is equal to, P real is equal to P ideal is equal to P real plus AN square by V square. This is the greater one. P ideal is equal to P real plus. This is the correction factor. What correction factor? Correction for pressure. What is the correction for pressure? Based on molecular attraction. So the two correction terms introduced in van der Waals equation is what illustrated now. Right? All these graphical representations you need to meticulously evaluate. You see that this is what I have written now. P ideal is equal to P real plus AN square by V square, which is the correction terminology. And the term compressibility factor, very important one. Compressibility factor. This is compressibility factor. Compressibility factor is equal to Z equal to PV by nRT. Compressibility factor means PV by nRT. We know ideal gas equation. PV is equal to nRT. Therefore, PV by nRT is equal to 1. So, Z is equal to 1 for ideal gases. Z is equal to 1 for ideal gases. For non-ideal gases, real gases, Z will not be equal to 1. There is a graphical representation similar to what we have seen, need to be analyzed clearly. This is the graph. You see that? Compressibility factor along the y-axis and pressure along the x-axis. This is ideal gas. You see, Z is equal to 1. This is ideal gas. And all gases tend to start from ideal point. But when the pressure increases, see, it's okay, they are ideal at low pressure. When the pressure increases, they start deviating from their character. Nitrogen, hydrogen, oxygen, methane, carbon dioxide, all act as real gases. Is it clear? Is it clear? And now the probable last important topic from the chapter. It's very important topic. Liquefaction of gases. Liquefaction of gases. Liquefaction of gases and an experimental studies based on Andrews isotherm. Andrews isotherm. Maybe you are aware of this particular graph, Andrews isotherm. This is what we are going to have a review, Andrews isotherm, right? See, the experimental studies based on liquefaction of gases was done. Before that, let us try to understand how do we liquefy a gas? How do we liquefy a gas? What are the conditions we apply? To liquefy a gas, we are doing mainly two things. Number one, we are reducing the temperature. We try to cool the gas. The temperature is reduced. Number one. Number two, we compress the gas. By reducing the temperature, by cooling the gas, and by compressing the gas, we are getting the gas to be liquefied, right? And this is investigated, experimented by Andrews and is called the Andrews isotherm. Suppose we are taking pressure volume graph, PV isotherm. At a particular higher temperature, this is PV diagram. At a higher temperature, for example, if you are analyzing about carbon dioxide, he was studying carbon dioxide. At a high temperature, say for example 60 degree, 50 degree, like that, the graph is like this, for example 60 degrees Celsius. At 50 degrees Celsius, the graph will come like this, at 50 degrees Celsius. At 40 degrees Celsius, it is the graph coming like this, which we have already discussed. As the temperature decreases, the graph is coming down. As the temperature decreases, the graph is coming down. And you know, at a particular temperature, say for example, carbon dioxide, somewhat in the range of 30-31 degrees Celsius, somewhat in the range of 30-31 degrees Celsius, the carbon dioxide starts liquefying. You can see a deflection like this. That is the critical point. We call it as critical temperature. Critical temperature. Somewhat 30-31 degrees Celsius. Approximately. At that temperature, we can see the liquefaction of carbon dioxide starts. Every gas will have a characteristic critical temperature. What is meant by critical temperature? The temperature above which a gas cannot be liquefied, or the temperature from where onwards the gas starts liquefying. The temperature on or below the gas starts liquefying. The temperature above which the gas cannot be liquefied. That is called a critical temperature. So this is the point where there is a deflection starting, and beyond that point, if you try to come, the graph obtained is somewhat like this. It is somewhat like this. Again, lower temperature, the graph obtained is somewhat like this. Again, the lower temperature, the graph obtained is, see, he was able to plot a region of liquefaction. This is called a region of liquefaction. This is a region of liquefaction, liquefaction region. Every gases we can have a liquefaction region. It is from this point onwards, below this temperature, the liquefaction starts. And the liquefaction starting temperature, we call it as critical temperature, TC. The temperature above which a gas cannot be liquefied. All these temperature, it will be gaseous state. Imagine initially I was here. Imagine initially I was here, point A. It is a gas. Now what I do is, I reduce the temperature. I am reducing the temperature and I am reaching somewhere here. This is point B. Again, there is gas. It is gas. Now we are compressing the gas. We are compressing means we are reducing the volume. When compressing, the volume reduces and the gas travels all the way here and it reaches the point C. At C, the liquefaction starts. At point C, the liquefaction starts. And from there is a rapid decrease in the volume. And C to D, this is liquefaction region. C to D is the liquefaction region and D onwards it is liquid. So this is liquid region, this is liquid gas interface and this is gas. Here all gases, this is gas, this is the liquefaction starting point and this is liquid gas interface and this is liquid. So what all things we did? We were here as a gas. We have reduced the temperature, cooled the gas. Now compress the gas. Upon compressing, we are reaching at the point. So we were at A. By cooling, we reached at B. By compressing, we reached at C. And C to D, it is a rapid decrease in the volume. Means the gas is converted to liquid. And by D, the liquefaction is over. And from there, it is in the liquid state. This is Andrews isotherm. This can be done in another way also. This can be done in another way also. Suppose I am at a point A, I can compress the gas. See, I'm compressing the gas and I will reach somewhere here. And straight down by cooling, I'll be reaching at liquid state. You see that? We can reach to liquid state. By compressing, I will travel all the way there. And by cooling, I will reach into liquid state. But there is no liquid gas interface. If you are traveling through liquid gas interface, first you will be cooling the gas and then compressing the gas. Right? It all happens based on a critical point. This is called a critical point. The temperature called the critical temperature and the pressure equivalent called the critical pressure and the volume equivalent is called the critical volume. And they are called the critical parameters. Critical parameters, right? Critical parameters, TC is equal to 8A by 27 RB and PC is equal to A by 27 B square and VC is equal to 3B. These are critical parameters. Critical temperature TC is equal to 8A by 27 RB. Van der Waals constants are involved in that expression. PC is equal to A by 27 B square. And VC is equal to 3B. These are critical parameters. Critical parameters. What is critical based on critical temperature? What is critical temperature? The temperature above which a gas cannot be liquefied. Right? That is regarding liquefaction of the gases, one of the most important area from the chapter. Now, a few talk on liquid state of matter. In liquid state of matter, what we discuss is vapor pressure, boiling point, surface tension, viscosity. These are small topics based on a few properties based on liquid state of matter is our next topic to wind up the discussion. So, it is vapor pressure and boiling point of liquids. Vapor pressure and boiling point of liquids. I think many of you know vapor pressure and boiling point are related terminology. Right? What is the definition of boiling point? What is the definition of boiling point? Boiling point is defined as the temperature at which vapor pressure of a liquid becomes equal to external pressure, atmospheric pressure, right? The boiling point of water is 100 degrees Celsius. Boiling point of water is 100 degrees Celsius. What does that mean? At 100 degrees Celsius, vapor pressure of liquid water becomes equal to 1 atm, that is external pressure. And then the liquid starts boiling. Is it clear? What is vapor pressure? Vapor pressure means the pressure offered by the vapor particles over the surface of the liquid. Every liquid will have an evaporation tendency. Every liquid will have an evaporation tendency, which basically depends on the nature of the liquid. A more volatile liquid will have an easy evaporation. When they evaporate, the vapor particles are settling over the surface. The pressure offered by, especially in a closed system. If it is in a closed system, the vapor particles settling over the liquid surface will impart a pressure on the liquid surface, which we call it as vapor pressure. So vapor pressure is defined as the equilibrium pressure offered by vapor particles over the surface of the liquid, which mainly depends on the nature of the liquid, number one, and also temperature. When the temperature increases, average kinetic energy of the molecules increases, their evaporation increases, vapor pressure increases, increases. Ultimately, when it becomes equal to external pressure, the liquid starts boiling. Okay, so vapor pressure and boiling point, very important terminology connected to liquid state of matter, which is well explained in the detailed explanation given in the NCERT, which you can go through. And don't forget to review such important points: normal boiling point and standard boiling point. What is the difference between normal boiling point and standard boiling point? Normal boiling point means at 1 atm pressure, it is normal boiling point. 1 atm pressure, it is normal boiling point, while 1 bar pressure, that is standard boiling point under standard condition. Standard condition, earlier STP standard means 1 atm is STP. And now the new standards, the pressure standard is 1 bar. So there is a slight difference. And that will reflect in the boiling point also. Standard and normal, it will reflect in the values also. You see, the normal boiling point, everybody know 100 degrees Celsius. That is a normal boiling point. That is at 1 atm pressure. While at 1 bar pressure, the boiling point is slightly lower, because 1 bar is 0.98 atm. So slightly the temperature will also come down. Next, a topic on surface tension. All of you know what is surface tension, what is surface energy. Every liquid surface, the liquids try to maintain a minimum surface area due to surface energy. The molecules in the surface will experience a net energy, which is called which is the reason for that surface tension. Everybody know it's a function of temperature. You see, the molecules in the interior of the matter, a molecule in the interior of the matter is different from a molecule in the surface, right? So surface molecule, the net attraction into the liquid, it is experiencing a force of attraction in all direction except the top. While a molecule in the interior, it is experiencing a force uniformly throughout around the other molecules. So a molecule at interior and a molecule at the surface will have their characteristics slightly different, based on which we define what is surface energy and surface tension. A very important property reflecting on various characteristics of the liquid state of matter and various unit also. You see, the definition for surface energy is explained here. The energy required to increase the surface area of liquid by 1 unit called the surface energy, and the unit joule per meter square. Joule per meter square. And the surface tension defined as force acting per unit length perpendicular to the line drawn, indicated by this and its dimensions. A detailed study happens in physics. I don't have to explain these things to you. Our main point of this application, fire polishing of glasses by heating, we make it a round, almost semi-spherical character by heating. Fire polishing of glass based on surface tension. These applications you must specifically note down. And finally, a temperature dependence influence also. A temperature dependent influence also. The increase in temperature increases the kinetic energy of the molecules and effectiveness of intermolecular attraction. So with increase in temperature, surface tension decreases. And a detailed discussion happens, the involvement of surfactants, detergents and soaps, how it is influencing. That's a different case we learn in another area. And then viscosity. Viscosity, another topic detailed learned in the physics area. What is laminar flow? How the liquid is flowing by layer, how the one layer flow influences the next layer. What is the velocity gradient explained? Right? A topic well explained, and see, this is called a laminar flow. This is called a laminar flow. This is one layer flow, and the immediate top and bottom layer will be influenced by a friction, a flowing friction, which we call it as basically a viscous friction, viscous force. So the upper layer is, you see the diagram. The middle layer moving with a velocity u, the upper layer moves with a velocity u plus du, a slightly higher velocity, while the lower layer is moving with a slightly lower velocity u minus du, right? And it is marked the interplanar distance dz, and du by dz, it is called, all of you know, that's velocity gradient, velocity gradient. And this is a law connecting viscosity. The force is proportional to, see the velocity, if the velocity of layer at a distance d is changed by a value du, this is called a velocity gradient. A force is required to maintain the flow of layers. A force is required to maintain the flow of layers. This force is proportional to area of contact. The force needed to maintain a laminar flow, it is directly proportional to area of contact and is also proportional to velocity gradient. Du by dz is velocity gradient. A, the surface area of contact, and F is equal to eta A du by dz. Eta is called the coefficient of viscosity. Coefficient of viscosity, a very popular terminology. I'm sure these are the topics well discussed and explained, and various problems that you do in physics classes. Don't forget to note down the coefficient of viscosity, its unit. The unit, Newton second per square meter or Pascal second. A very important unit there, Poise, known after Jean-Louis Poiseuille. Greater the viscosity, more slowly the liquid flows. You might have seen some of the questions regarding glass. Glass to be called a supercooled liquid. Glass is not a perfect solid. Glass is not a perfect solid. It is a pseudo solid. It's a pseudo solid. It is called a supercooled liquid. And they have a tendency to flow. According to the weather changes, glasses can have a tendency to flow. That is why it is so explained. But I've seen in some questions, the bottom layer of a window pan, glass window pan, seem to be thicker over the course of time, years or years. Over the course of time, it becomes slightly thicker due to a flowing tendency which is affected by the environmental temperature changes and all. It's a pseudo solid, highly viscous liquid which resembles the property of a solid. And the last point, effect of temperature. Same thing, like surface tension, viscosity also affected by temperature. When the temperature increases, viscosity decreases. Effect of temperature. So that is a few property regarding liquid state of matter. Major discussion happened on gaseous state. We started from intermolecular forces of attraction, various intermolecular forces. Then gas laws, Boyle's law, Charles' law, Avogadro's law, ideal gas equation. Dalton's law of partial pressures, density formula, kinetic molecular theory of gases, and kinetic gas equation. PV equal to 1 by 3 mn u square derived into Ke is equal to 3 by 2 RT. Kinetic theory of gases, various molecular velocity terms and relationships, right? And then real gas equation, Van der Waals constant A, Van der Waals constant B, its units, applications, right? Correction factor for pressure, correction factor for volume, compressibility factor and the related graphical representation, and then liquefaction of gases, Andrews isotherm, then the properties of liquids, vapor pressure, boiling point, viscosity, surface tension, etc. These are the brief idea from the chapter 5, states of matter. Okay, we'll meet with another chapter in another video. Till then, bye, see you.